The very first thing we want to do in a physics class is to describe how objects move. So we're going to start out restricting our object to move along a straight line. So if my object is this car, we're going to say, okay, it can move back and forth along this straight line, but it's not allowed to move up or down or left or right. It can just go forward and backwards along the line. All right, so later we'll talk about what happens when you can move in multiple dimensions, but this is motion along a straight line. Okay, so our first thing is just to say where the object is, to find its position. In order to do that, we need a coordinate system, because I can say, oh yeah, the object's right here. But right here might not be particularly helpful if I'm trying to describe that to somebody else. So if I want to describe it to somebody else, we need to collectively agree on a coordinate system. So a coordinate system needs to have a 0 point. So let's say that this is my 0, and this is the positive direction. So we'll decide that moving to the right is positive and moving to the left is negative. And then we can start marking off our distance, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 meters. And I could say that right now, this car, the front of the car, is at approximately the 5-meter mark. That would be its position. Okay, so position is just where the car is right now, where the object is right now. That's pretty straightforward. The next thing we want to talk about is displacement. And I guess let's just say position. In one dimension, position we usually describe as x. That's the current location of the object. And that, of course, is measured in meters. The next thing we're interested in is displacement. And displacement is something that happens over a period of time. So we have a starting time and an ending time. So if we have this object and it starts here at the 5-meter mark, and then it moves over here to the 9-meter mark, we can say that its position has changed, and therefore it has a displacement. Displacement is defined as your final position minus your initial position. And of course, this is also measured in meters. So in this case, if my final position was 9 and my initial position was 5, we have a displacement of plus 4 meters. We could also have a negative displacement if my car started at the 5-meter mark and then it moved to the 2-meter mark, so that my initial x was here and my final x was here. We could have a final position of 2 and an initial position of 5, and 2 minus 5 is a displacement of negative 3 meters. And again, if we imagine that the car started here, a positive displacement means we moved this way, and a negative displacement means we moved that way. Okay, that's great. So we understand displacement and position. Those are sort of the easiest things to describe about an object. But what if the object is moving? If it's moving, then it has a velocity. Okay, and we can start out with the definition of average velocity. And the average velocity is just the distance you traveled, that is, be your displacement, divided by the amount of time that it took, the change in time. So this is actually a really interesting definition. It means that if we start at the 3-meter mark and we go forward and then we go backwards and we go forward again and then we go backwards again and then we go back here and then we end up at the 9-meter mark. I forget where we started. Let's say we started at the 2-meter mark. So our initial position was x equals 2, and our final position was x equals 9. That means our displacement was plus 7 meters. And let's say that took 3 seconds. We would find our average velocity by looking at our displacement divided by our time. Notice everything that happened in between was irrelevant. All that mattered is where did we end up and where did we start. So the fact that sometimes I was going forward, sometimes I was going backwards, sometimes I was going forward again, none of that matters. All that matters is where did we start and where did we finish. So average velocity is defined as displacement divided by time. Now I want to try to imagine what a graph of that motion would have looked like. So I started at 2 meters and I went forward, which means my position increased, and then I went backwards, which means my position decreased, and then I went forward again, and then I went backwards again, and then I went forward again, and we started at 2 meters, and we ended up at 7 meters. So this was our starting location, and this was our ending location, and this whole trip took 1, 2, 3 seconds. And so if I were to graph the position of the object in meters as a function of the time in seconds, we might get a graph that looked like this. And when we find the average velocity, what we're doing is we're finding the displacement, which is the final position, minus the initial position, divided by the change in time, which is the final time minus the initial time. So what we're sort of doing is we're finding the slope of a line that connects those 2 points. Now, I realize my line didn't do a good job of connecting those 2 points. Again, okay, we are finding the slope of a straight line that connected those 2 points. So the rise of this line is the displacement plus 7 meters, and the run is the change in time, which is 3 seconds. The change in position was 3 meters. The change in time was, the change in position was 7 meters. The change in time was 3 seconds. And so the average velocity was the change in position divided by the change in time, or the displacement divided by the change in time. Okay. But what if I want to know how fast the car was moving at this particular moment in time? So what I would do is I would say, okay, well, let's find its position now, x initial, and its position a moment later, x final, and then we could find the average velocity between those 2 points. And that would be pretty close to my velocity at this point. But to get a better estimate of my velocity at this point, we should pick 2 points that are closer together. So instead of picking this as our x final, let's pick something that's even closer as our x final. And then the slope of this line would tell us a better estimate of the velocity at x initial. But if we want to do even better, we should take an even smaller period of time. And so velocity at a given point is actually a limit. It's the limit as delta t goes to 0 of the position at t plus delta t, that is my final position, minus the position at t divided by delta t. And if you have started your calculus class, and if you've gotten very far at all, you've maybe seen this as the definition of a derivative. And so what this means is that velocity is equal to the derivative of position with respect to time, dx dt. So we can write this several ways. We can write this as the derivative with respect to time of the position function. We can write this as dx dt, or we can write this as x dot of t. X dot means the derivative with respect to time. And all of these will be equal to the velocity of the object. So velocity is the derivative of position. It is the rate of change of position, how quickly the position is changing. And notice the velocity can be negative, which means that the position is becoming more negative, or the velocity can be positive, meaning the position is becoming more positive. A positive velocity means that the object is moving in the positive direction. A negative velocity means that the object is moving in the negative direction. Okay, last thing we need to talk about is acceleration. So if we have a moving object, it can move at a constant speed. If it's moving at a constant speed, its acceleration is 0. But it could also be speeding up, or it could be slowing down. So if it's speeding up or slowing down, then the acceleration is not 0, and acceleration, average acceleration, is defined as the final velocity minus the initial velocity divided by the change in time. So like velocity tells us how quickly the position is changing, acceleration tells us how quickly the velocity is changing. And we can define something called the instantaneous acceleration. That is the acceleration right now. And just like we did for velocity, this is going to be a limit. So the acceleration of an object is going to equal the limit as delta t goes to 0 of the velocity at t plus delta t minus the velocity at t. So that is the final velocity minus the initial velocity divided by the change in time. And that would be the instantaneous acceleration, or the acceleration right now. So that is equal to the derivative with respect to time of the velocity function. Or another way of writing that is dv dt, or another way of writing that is v dot. V dot means the derivative with respect to time of velocity. And because acceleration is the derivative of velocity and velocity is the derivative of position, that also means that acceleration is equal to the second derivative of position. Or another way of writing that is x double dot, the second derivative of position with respect to time. All right, so those are the definitions of position, velocity, and acceleration, and I'll see you in the next video.